Let's move on now from our discussion about mechanisms to talking about the reactivity of carboxylate derivatives. The way this is going to work is we're going to go through each derivative one at a time, starting from the most reactive to the least reactive, and we'll also talk about some other derivatives that behave like carboxylic acids throughout. So we're going to start out with the preparation of acid chlorides, as these are the most reactive of the carboxylate derivatives that we're going to discuss. The way that we prepare the acyl chloride is from carboxylic acids. We're going to treat them with SOCl2, a reagent you might remember from Organic 1. This is called thionyl chloride. Here's the structure. In combination with pyridine, which is this heteroaromatic nitrogen compound. Thionyl chloride in this reaction acts as a very, very good electrophile. In fact, it behaves a lot like an acid chloride. The purpose of pyridine here is that this is a relatively non-nucleophilic base, which is going to mop up hydrochloric acid, which is produced over the course of this reaction. The reason why we might want to remove hydrochloric acid over the course of this reaction is that hydrochloric acid can cause many side reactions to occur with other functional groups, which we want to avoid. There are some other byproducts from this reaction. One that's produced is SO2, and pyridinium chloride, the conjugate base of pyridine, is what we get out of this reaction as well. SO2 is a gas at standard temperature and pressure, so this will bubble out of the solution. Pyridinium chloride precipitates as a solid. Both of these help drive this reaction to completion. This reaction is very, very efficient and usually extremely high yielding. For practice here, try proposing a mechanism for this reaction. So we'll give you a little guidance as far as the mechanism is concerned on this. This reaction happens in two stages. First, the carboxylic acid reacts with thionyl chloride to generate this extremely good acyl leaving group. This is also the step where we generate the conjugate base of the conjugate acid of pyridine, pyridinium chloride. In the second step, this acyl derivative will react with chloride ions to produce our acyl halide, SO2 gas, and another chloride ion as a leaving group. Propose a mechanism for each of these stages in turn, then check your work. The mechanism for this reaction can be found in Klein on page 918. So next, let's go over some of the reactions of acyl halides. To start, we'll discuss their reactions with weak or moderate nucleophiles. Some of this we've already practiced mechanisms for in the past. Starting from an acyl halide, we can make carboxylic acids, esters, and amides. So take a moment here and think through these reactions and propose reagents for each of these steps. So some of these we've seen before, but let's talk about them anyway. If we wanted to convert an acyl chloride back into a carboxylic acid, we would add water combined with pyridine. This is known as hydrolysis. Again, the pyridine here serves to mop up any excess HCl that's formed during the reaction and prevent side reactions from happening. Analogously, if we treat an acyl halide with an alcohol in the presence of a base like pyridine, we will get an ester. This is called alcoholysis. Finally, to make amides, which is sometimes known as aminolysis, we can treat our acid chloride with an excess of our amine. Here, the reason why we're using an excess of the amine is that one equivalent will act as a nucleophile, the second equivalent will act as a base. In this case, when we're using ammonia as our nitrogen source, it's fine to add an excess, as ammonia is relatively inexpensive and readily available. If, however, we had an amine that was more complex or more expensive, we might want to use one equivalent of our amine and use a non-nucleophilic base like pyridine to absorb the excess HCl. If you want more practice here, show the mechanisms for each of these transformations. How about reactions with strong nucleophiles? Specifically, when we're talking about strong nucleophiles in this case, we're referring to carbanions and hydride ions, added either as Grignard or organometallic reagents, or things like lithium aluminum hydride. We spoke about this briefly back in Organic 1. If we take an acyl halide and we treat it with either lithium aluminum hydride followed by a proton workup, or an organometallic reagent followed by a protonation workup, we will get either a primary or a tertiary alcohol respectively. These two reactions are very difficult to stop, and we'll always end up absorbing two of our nucleophiles rather than just one. Now in Organic 1, we sort of waved our hands at this and said, you just need to know that this happens, but now we're better equipped to talk about the mechanism of the process. So if we treat an acyl halide, which is a very reactive electrophile with a strong nucleophile like a hydride ion, we'll very quickly have a reaction to produce a tetrahedral intermediate. This intermediate will collapse producing a ketone if we have a carbon nucleophile, or an aldehyde if we have a hydride nucleophile. Now, since ketones and aldehydes are still reactive under these conditions, it's very, very difficult to stop this reaction at this stage. So another equivalent of our nucleophile will add, forming an alkoxide ion. So clearly this is a useful transformation. So what's the solution to this? Well, the solution is to try to find a more moderate source of hydride ions and carbanions, ones that can only react with the more reactive acyl halide, but not react with the less reactive ketone or aldehyde. For hydrides, we're going to use this reagent here, which is lithium aluminum tri-tert-butoxyhydride. This compound is much less reactive than lithium aluminum hydride, in large part because of the bulkiness of the alkoxy groups that we've added on. For carbanions and carbon nucleophiles, we're going to use reagents like this. This is known as a lithium dialkyl cuprate, also called a Gilman reagent. Here, the copper, which is a larger, softer atom, means that we've produced a less reactive carbon with a partial negative charge. Both of these can react with acid chlorides, but they will not react with ketones and aldehydes, giving us selective reagents. For example, if we take this compound, which has both a ketone and an acid chloride, we can treat it either with our hydride reducing agent or with our Gilman reagent to react only with the acyl chloride, producing either an aldehyde or a ketone as a product. Note that there is no workup here. Since we don't have an alkoxide ion produced as a product, we do not need to add a proton after the reaction is done, and that these reactions are selective and only react with the acyl halide. These reagents, unlike lithium aluminum hydride and Grignard reagents, are broadly tolerant of other functional groups, including ones with acidic protons. Gilman reagents can be prepared also from scratch, so to speak. They are prepared from organolithium reagents and copper-1 iodide. So the treatment of copper iodide with two equivalents of an organolithium reagent will give the corresponding Gilman reagent, R2CuLi, and lithium iodide as a side product. Let's do some practice with these reagents. So I'm about to show you a reaction flowchart, and what I'd like you to do here is complete the flowchart. Fill in every reagent for each part of the connecting flowchart that you possibly can. So pause the video, take plenty of time to do this. What I'd ask is that when you first do this, try to do it from memory only. After you do it from memory, check the book to see if you're missing any reactions and fill those in. Here's your flowchart. Take a few minutes to fill in as many of the arrows on this flowchart as you possibly can. Let's discuss this. For starters, we can convert the carboxylic acid to an acyl halide using thionyl chloride, with or without pyridine. The acyl halide can be converted to an ester by treatment with alcohol and pyridine. Ketones can be made with Gilman reagents. Tertiary alcohols can be made with the more strong and more difficult to control organometallic reagents. Aldehydes can be prepared with our new reduction reagent, a lithium aluminum tri-tert-butoxyhydride. Amides can be prepared with an excess of the corresponding amine. Primary alcohols can be prepared by our old method by treatment with lithium aluminum hydride followed by workup with water. And acid chlorides can be made back into carboxylic acids by hydrolysis with water in the presence of pyridine. Now, you may also have noticed that there's some other connections that can be made on this diagram as well. So, for instance, the carboxylic acid can be formed from the primary alcohol, or the primary alcohol can be made from the carboxylic acid by the appropriate redox reactions. We can also make connections with the aldehydes and several other instances on this diagram. We'll be able to fill in even more reactions as we continue talking about different carboxylate derivatives. That's all for acyl halides. Next time we'll be talking about acid anhydrides, which react very similarly to acid chlorides.